Hi guys, we're going to have a look at Euler's method of solving differential equations. It's a very interesting technique, but you need to watch very carefully because it can get very confusing. It's an approximate technique and it is an iterative method which is applied. So please make sure you've got a good mind when you have a look at this and you're clear and focused. Maybe have a nice cup of tea and sit down and relax and we'll go through it, okay? Now, Euler's method for solving DEs. What is it? Well, it's a numerical estimate of the graphical profile of a function, determined iteratively, point by point, from its gradient function, and one known point on the original function. Not the gradient, the original function, that one known point. So you've got one known point on the original and you've got the equation for the gradient function, okay? Why is it used? Well, it's used because some functions cannot be integrated analytically because they are just too complicated. Yep. How does it work? Well, here it comes. It works by using small iterations of x, over which the gradient is assumed to be constant. It's assumed to be constant, no curving of the graph. Okay, so if you use a very small change in x, iterations of very small changes in x, it's probably better to say there, over which the gradient is assumed to be constant to approximate the corresponding next value of y in turn on an iterative basis, okay? But it's very important to use small delta x's, small little bits, little increments in x, okay, for this procedure, because otherwise it becomes blindingly inaccurate, okay? I'll show you on the next page with a graph. The procedure is repeated iteratively over a defined x domain from a known starting point on the original function to build up an approximate profile of y values, which then can be plotted or they can be tabulated. Okay, now that might not really sink in properly, but when I do this on the next screen, you're likely to get a better idea of it. So here's the concept shown graphically. Okay, we've got now, this is a known point here on the original function, and we have to assume here that the curve of the original function is not actually known. It's not actually known. It's just drawn here to illustrate the process, okay? Just drawn here to illustrate the process for you. So you have to assume that all you know is the gradient function and this green known point on the original function. Gradient function plus one known point. So the gradient at each point is known because we have the gradient function. Now, the method, here we go. 1. You draw a tangent line over a small distance of delta x, or h as it's otherwise known, from the current operating point, which in this case is here. That's where we're starting. That's the one point we know on the original function. You draw a tangent out from there, okay? And there it is, okay? Now, this gives our new estimated point on the curve. Now you can see it's wrong because the curve curved, but we're assuming it doesn't curve, okay? We're assuming it's linear over a very small increment in x, okay? That's the procedure, and you just iterate that procedure. So basically, what we then do, there's our h, which is our delta x, over which we've done this particular step in the calculation. Secondly, we then use the new gradient at the current new x location, which will be here, okay? We recalculate the gradient because we know the gradient at this point. We just don't know what the original function, where it is at this point. But we know what the gradient is because we've got the equation for it. Okay, so you start here, use the gradient at this location of x here, and you draw a new line segment over that small h. Okay, like that. Okay, get it? And that way we're building up a profile of the curve. Okay, there's our new delta x over which we did that estimate of where the curve's going to go from here to there, okay? But using a different gradient at this point. That's why this line here's got a slightly different slope to that line there. Okay? How are you going? Number 3, what we do is we repeat step 2 for as many steps as required to build an appropriate profile of the curve. Now just have a look. I'll do a few more for you. But NB, the smaller h or delta x actually is, the more accurate the result. Because you can see, you know, if you iterate it over very, very tiny increments of x, you basically don't get too inaccurate when you get to your next point determined from each iteration, okay? Yeah, you get that. Now have a look at this graph there. I'm doing that, and I'm doing that, okay? See, now this is the profile of individual points of y, estimated points of y, on this curve using this procedure, and you can see that they're not really accurate. That's the accurate curve, but we don't know that curve. We only know the gradient function, which is too complicated to integrate analytically. Okay, I'm using a very simple example here just to illustrate the process. Okay, all right, how are you going? Now this technique gives an estimate only, as I've just said a few times. It assumes no curvature at all of the graph itself, the original graph, the parent graph, over h. But of course that's going to be wrong for the vast majority of curves which curve. Yes, in fact all curves which curve. There you are. Now you see that? In that case there, we've basically, we've got an estimate. That's x2. If that's x1, y1, this is x2 and y2 estimate. You can see it's wrong. It's actually an underestimate of what's actually happening there. Yeah, that's x2 and y2 actual there. See that? Okay, so now M1, okay, M1 here, M at 1, the gradient at point 1 is equal to y2 est minus y1 over h. Isn't that right? That's right, y2 minus y1 over x2 minus x1, and x2 minus x1 is h. Get that? Okay. Therefore, y2 estimate, guys, if I make that the subject, will be y1 plus h times m1. Now, that is the formula we use to guesstimate or approximate the value of y2 estimate. Take the value at y1, which, when we're starting off, that's the one value that we do know on the original curve. It's given to us. Then you add that, the small increment of x or delta x or h times the gradient at point 1, which you can work out from the formula, okay? The gradient at point 1, and it's times that h to get our new estimated point at x value 2. y2 estimated equals y1 plus h times the gradient at the previous point, in this case point 1. Okay, that's the formula. That's Euler's formula for this estimate, okay, the Euler method for solving DEs, yeah? Now in general, we've got here, in general, yn plus 1 equals the previous value yn plus the x increment, or h, times the gradient at the previous value of x compared to this point here that we're trying to work out, okay? So yn plus 1 equals yn plus h times the gradient at where x is n. Alright? That's it. That's what you use to work out this point from that point, and then from this point here from that point, and then this point from that point, and this point from that point, and so it goes. Okay? That's how you do it. Now, that formula is incredibly important. You have to know that formula. That is it. That is Euler's method in a nutshell. Now here's an example using tabular format for computation, which I find very useful and very systematic. I prefer this rather than just using straight formulae all the time. So you see what you think about it. I really like it. I don't think it's very common for people to use it, but I don't know why. I think it's great. So assume we cannot find this integral. Assume that that's too hard to analytically do that, right? The integral of 2x is just too hard for us, right? So we do know, however, that on the original function of which the after you did integrate this, if you could do it, you do know, the only thing you know about the original function is that when at the first known point that we're going to extrapolate from, x is 0 and y is 1, right? Coordinate point 0 and 1. And we require y when x is 1, okay? So we've got y when x is 0, we need y when x is 1. So we've got to iterate somehow between x is 0 and x is 1, because we can't work this out, right? We can't work it out, you know, which is rubbish, but we're just assuming that so that for the sake of the exercise for me to demonstrate it to you. So we know that dy dx is 2x, yes? Case 1. Now I'm going to do two cases for you when h can be 0.2, in which case there'll be 5 iterations, okay, to get over a span of x changing by 1 whole unit. And then we're going to do h is 0.1, in which case there'll be 10 iterations. And it'll be more accurate when h is 0.1, but there'll be more iterations for us to do. That's always the trade-off, you know, more work to get more accuracy. So here's a table. We've got n, we've got x at n, we've got y at n, then we've got dy dx when x equals x at n. Now, we're leading up to Euler's formula now. There it is, okay? So we know that, just to make it clear again, gradient equals rise over run, therefore run times gradient gets rise, okay? That's Euler's technique there. It's an estimate, right? It's really, I probably should have a curly equals there to make sure it's where we understand this is just an estimate, okay? It's not accurate, it's an estimate. So therefore, in the next column, we say, okay, the new value of y in the next row, starting value of y, will be this value of y here, plus this estimated rise in y. That'll be our estimate of y at n plus 1, which carries over into this cell here. Okay, that's what you do, and then you iterate all over again until you do the correct number of iterations to get the value of y estimated when x is 1 in this case. So there's our values of n. Here's our values of x. They're going to be the values of x. Yes, you get that? Now, we do know that y is 1 when x is 0. That's given to us up there. So we're just going to go through the iteration. Now, dy dx is 2x, yes? So therefore, when x is 0, dy dx is going to be 2 times 0, which should be 0. Now, if we multiply that by h, right, that's still going to be 0, because h is 0.2. That's still going to be 0. So therefore, our new estimated value of y, it's all a little bit of a yawn, is 1 plus 0. Because that's what we got for our rise, estimated rise in this row, which will just be 1. Okay, and that carries over. That carries over into this second row. Now, we've got x is 0.2 now, and y is estimated to be 0.1 as a, oh, not 0.1, 1 I mean, as a carryover from this previous exercise. Yes, now, let's do another iteration, guys. So therefore, dy dx when x is 0.2 is going to be 2 times 0.2, which should be 0.4. Therefore now, h times that value will be, what will it be? Yeah, 0.08. So therefore our new estimated value of y after this iteration will be 1, which was the starting value here, plus the estimated rise over this increment in x, which should be 0.08, so we get 1.08, and that value carries over to the next iteration. Are you getting this now? Yeah, you're starting to get into the rhythm of it now. So dy dx when x is 0.4 would be 2 times 0.4, wouldn't it? Which would be 0.8, and this baby here would be 0.2 h times 0.8, which would be, what would that be? It would be 0.16, oh, I'm going too fast now, sorry about that, 0.16, and therefore this new value of estimated value of y would be 1.08 plus the 0.16, which will get you 1.24, and that value carries over again. Now we do the whole thing again, and it's like watching grass grow, but I want to show you so that you will get this, right? Now, come on, you do this now. Come on, what do we got? 2 times x, which is 1.2, isn't it? Yeah, 2, that's 1.2. Now we're going to do h times that 1.2, and we're going to get 0.24. Now we're going to add that 0.24, which is your delta y, onto the original y, and we're going to get, what are we going to get? 1.48, and that carries over now to the next row. Oh goodness, we've only got one more to go, haven't we? One more iteration. Thank goodness for that. So, okay, now 2 times x, where x is 0.8, is 1.6, yes? 1.6 times h, which should be that, will get us that. Now we add that delta y onto the original y, and we get that, and it gets us to that. Now that looks like it, guys. That carries over to the next thing, and that's our final estimated value of y when x is 1. Okay, it's 1.8. Good heavens above. Okay, now you know how to do it, alright? Now you know how to do it. So when x is 0, y is... wait a minute, that's wrong. Just a moment. Abracadabra. That should have read x is 1. Y is estimated to be 1.8. Okay, so now we've got it. Thank goodness. Now I'm going to do it analytically for you, just to show you how wrong that estimate is. Okay, because we can do this one analytically, and it's a good exercise to do just to prove how inaccurate is the estimate, right? So we know that y actual would be, what would it be? Yes, it would be 1, which is the value of y when x is 0, plus the integral of the whole thing from 0 to 1. Yes, and that's easy to do. That's 2x, that's just going to be x squared, isn't it? So, yeah, x squared integrated between 0 and 1, which will get us 1 plus 1, which will get us 2. So the actual analytically correct value of y when x is 1 is 2. We estimated with Euler's technique to be 1.8, which ain't too crash hot, guys. That's not very accurate, is it? No, Mr. Wolfman, it's pretty bad. So, to increase the accuracy, we need to make h smaller and proceed in smaller steps. Smaller steps, yes? Now, I'm going to do that over the page. It's nauseatingly boring, but I will do it quickly, okay? I'll just fill out the numbers. Maybe you'd like to do it. Maybe you'd like to pause the video now and do it. And then I'll fill in the numbers and you can see how you went. Go on, you go away and do that now, okay? I'll see you in a minute. Alright, you're back? Okay, hello there. Welcome back. Now, we'll just do it, okay? I'm just going to do it quickly for you because I can't, it'll be like watching grass grow. So that's the x values. Now, I think I'm going to do an abracadabra and fill it in for you, okay? Do you mind? So, and so on and so on and so on. There it comes. Oh, look at this. My goodness. It's fast, man. And we will get to... What will we get to? It's coming, it's coming, it's coming. Ah, there it is. 1.9. Now, did you get all that? Pause the video and have a look. Did you make a boo-boo anywhere? Well, hopefully you didn't. But that's what I got, and I checked it, so it's right, guys. So that's 1.9. Now, that's more accurate, isn't it? Much more accurate than what we got before with only 5 iterations. Yes, it's a much better result. So y actual is 2, as we found on the previous screen. Y estimate is 1.9 when h is 0.1, and y estimate was only 1.8 when h was 0.2. So you can see it's much more accurate when you reduce the delta x increment, or the value of h. Yes, now Euler's method can be done on CAS, and I'm about to show you that as a very stunning little exercise. And you can do any number of iterations on CAS because it just does it in a snap. And I'll show you the accuracy that you can get by using h's 0.01. Yes, I know, gasp. It's so exciting. I'll show you. Now, what you got to do, this is the syntax you put in on your TI CAS handheld device. Now, you go to the catalogue, which is the book. You go into tab 1, and then you select Euler from the catalogue, okay? Now, what do you do then, Mr. Wolfman? You type E to get the access to the the first entry of the alphabetical list, which starts with E, and then you scroll down to Euler till you find it. And this is the formula. When you get it, you hit enter, and that then appears on the screen. So this is dy dx. This first entry is dy dx, then you put a comma, and then you put x. Okay, that is the independent variable. Whatever the independent variable is, in this case it is x. Then you put the dependent variable, which in our case is y. Okay, no surprises there. So it's 2 times x, comma y, and then comma, and then what happens in those curly brackets then is the starting value of x and the finishing value of x, and you must use the curly brackets, otherwise it'll freak out and it won't work for you. Alright, now what's next is the starting value of y. Okay, when x was 0, you remember y was 1, and this next value is, yes, you guessed it, h. Okay, and what you get is this thing over here. It iterates and it works it out for you in an absolute flash. You get that, and you can see that our last value, our last estimated value, which is the estimate of y when x was 1, with 5 increments, is going to be 1.8. We did that manually, so we must have been correct, yes? Now, as h decreases, the accuracy goes up, because the assumption of linearity becomes a closer kind of thing, you know, as h goes down, the curve hasn't had a chance to bend away too much, so it's more accurate to assume linearity over a smaller increment of h than a larger one. Now look at this. look. This is where h is 0.01. Now, you're not seeing the full list here. I'm just showing you the right-hand tail end of the computer's spat all this out. When we got to 1, after 100 iterations, guys, because h is 0.01, it came up with 1.99. Now, I know, sigh, gasp, shock, horror, that is incredible. That's very, very accurate, because the real answer is 2. That's really good, isn't it? It's just amazing. Yes? Do you like it? 100 calculations. Yes, and we got that. So it's really, really good. So now, having done all that, now, are we overestimating or are we underestimating when we do this calculation? Well, it depends on the way the curve is curving, guys. For if the gradient is increasing as x increases, you're going to get an underestimate of the actual by using Euler, and that shows you the reason. See, we're going to be extrapolating out an assumption of linearity from a point here to a point from here, using this gradient to say here for our first increment, where that's h, that interval there is h. You get y estimate is there, but y actual is up there, so you underestimate if this curve is peeling away off here and the gradient is increasing. Get that? Yeah, and if the gradient is decreasing as x increases, the reverse happens. You get an overestimate. This diagram shows you why. You see? You're assuming linearity from this point here going up to there to get our estimate of y, but y actual is here because the gradient is decreasing as x increases. So that's an overestimate. Alright, you get that? That's the deal, guys. Now, some examination questions, but I'm going to leave that till next time. We'll do those next time in the next video. So please come back soon and we'll do those questions for you, because this is quite a long, complicated, arduous kind of exercise and I don't want to send your mind into a coma. Alright? So I'll see you soon. Bye for now.